Thanks for the intro. Like you said, I'm a postdoc at Mike Jewett's lab, but I work really closely with Marty Burke and his lab at UIUC. And I'm really thankful for the opportunity to talk and share my work engineering enzymes and pathways to try to develop a way to manufacture non-toxic antifungals. So amphotericin has served as gold standard for the treatment of life-threatening systemic fungal infections for more than half a century. And despite its high potency, relatively rare occurrence for resistance and broad spectrum activity, amphotericin is unfortunately highly toxic. And the effective treatment of those deadly fungal infections is often prevented not by a lack of efficacy, but by these dose-limiting toxicities. So because these systemic fungal infections represent a huge threat to human health worldwide, developing less toxic but equally efficient amphotericin analogs could really transform how we treat fungal infections. And recently, Marty and his lab had measured these key structure-function relationships that really revealed that amphotericin's toxicity can be attributed in large part to this unusual mycosamine sugar. And amazingly, if by switching a single stereocenter in that sugar, you can actually produce an essentially non-toxic but equally potent amphotericin analog. But despite the impact that this new amphotericin might have, the complexity of this natural product really makes designing a synthetic route to it very challenging, especially when you want to scale this to meet the world's need for an important broad spectrum antifungal. In contrast, bacteria are really good at making this compound. Amphotericin is routinely fermented on the metric ton scale, and even academic strains can produce up to 20 grams per liter. So we were really inspired by the biocatalytic power of these certain strains of bacteria, and we were wondering if we could somehow engineer them to make this non-toxic analog. And we kind of imagine this happening in two phases. So we could either go from in the first phase, we could develop this kind of three-step sugar swapping strategy using exclusively enzymes, whereby in the first step, we just remove the natural sugar enzymatically. In a second step, we string enzymes together to make a cascade that will produce our unnatural sugar that's non-toxic. And then in a third step, engineer a new enzyme that will transfer the newly made sugar in step 2 onto the product of step 1, and then complete the biosynthesis of our unnatural analog. And then importantly, we thought that we could, once we figure out all this enzyme chemistry, we could take an industrially relevant strain that produces amphotericin and just swap out the enzymatic parts, swap out the natural enzymatic parts for those that we've engineered, and in this way kind of take advantage of all the existing infrastructure that's used to produce amphotericin, but instead produce this non-natural analog. So with those kind of goals set, we began to tease apart each step in our biosynthesis. So in the first step, the idea is to remove the natural sugar and make large quantities of the A-glycone. So many glycosyl transferases that decorate natural products with sugars do so by using these activated NDP sugars as donors, and they expel these nucleoside diphosphates as a result of forming this glycosidic bond. And it's really well known that these enzymes can perform reverse reactions, essentially deglycosylating the natural product. However, NDP sugar formation is really thermodynamically disfavored, and they have KEQs of less than 1 and typically poor yields. So we needed a way to overcome this thermodynamic limitation. So one strategy we used was to use these promiscuous hydrolase enzymes that will metabolize the resulting GDP sugar, and they actually cleave the GDP from the sugar and essentially maintain high concentrations of our nucleoside diphosphate that will drive deglycosylation further. And that's shown in these two HPLC traces where we just run the reaction with just excessive amounts of GDP to push the reverse reaction. And then you can see that the yields of our amphoterolide, our aglycone, are increased when we include enzymes that metabolize that sugar and maintain that high GDP concentration. In parallel, we're investigating other ways of metabolizing sugars that might provide an even more efficient process for deglycosylation. So one way we might be able to do this is by using natural transaminases that transform this amine into this unstable ketone sugar that would likely degrade upon heating. And that might provide a suitable thermodynamic sink to pull deglycosylation using enzymes and heat. So the second step is actually making the unnatural sugar. So we've designed a couple of different routes and we like to categorize them as short-term and long-term solutions. So in one short-term solution, we've designed this kind of hybrid chemical enzymatic route that uses chemistry to go from really cheap and abundant starting materials to this really specific epimycosamine sugar with a nitrophenyl donor. And then a final enzymatic step can cleave off this nitrophenyl group and attach our GDP and or our nucleoside diphosphate and give us our natural or our ultimate substrate that we can feed to the enzyme. This provides a pretty quick and easy way to access these sugars for screening. It's also a flexible route. So a lot of glycosyl transferases use different kinds of nucleoside diphosphates as their activating reagents. So this gives us the flexibility to make a couple of variations of this compound and maximize our ability to find an enzyme that might be able to take one version, at least one version of this kind of sugar and transfer it on to our natural product. But this isn't totally enzymatic and it's not the ultimate solution that we're looking for. So we've designed two other routes that we're terming long-term solutions that are completely enzymatic. So in this first one, we've kind of assembled different enzymes from a bunch of different pathways and essentially assembled the epimycosamine sugar activated by a TDP nucleoside diphosphate. In parallel, we've also proposed that we could potentially engineer the natural enzymes that make mycosamine to just simply tolerate the epimerization at that 2' position. And that way we can make a pretty short route to our GDP epimycosamine. Now, if you notice, the TDP route specifically makes the TDP version, and our enzyme doesn't really like that nucleoside diphosphate. But hopefully, in the next slides, we might suggest that this could be good enough in the future. So the third step is now taking the sugar and the aglycone and finding an enzyme that can put them together. This third and final step is actually probably the most substantial challenge and where I've spent most of my time. And that's because the natural glycosyl transferase that transfers mycosamine onto the aglycone has absolutely zero activity for this epi sugar. So despite just this small structural change, it absolutely hates this substrate. And we're posed with the difficult challenge of engineering essentially a new function into the enzyme. So the way that we're going about doing this is by using a substrate walking or a in vitro coevolution directed evolution strategy that Huimin Zhao's lab actually kind of pioneered to overcome this strict substrate scope. So we have this kind of hypothetical evolutionary pathway where we first challenge the enzyme with one substrate, evolve it to be really good at that, and then move on to a structurally similar substrate and use these as kind of stepping stones ultimately to our epimycosamine sugar. So in a way, we're evolving the substrate as we're evolving the enzyme, and we're trying to lead it towards substrates that look more and more close to the ultimate epimycosamine sugar. And so to do this, we developed this cell-free directed evolution platform to prototype all of these mutant enzymes, where we're using different phases of random and rational mutagenesis to make libraries of our mutants. We can build those enzymes and express those enzymes using cell-free protein synthesis and using robotic and acoustic liquid handling to perform all that. And then we can test our enzymes with a given sugar. Either we know the sequences from the beginning, or we can sequence those mutants that perform well, or at least give interesting results, and then hopefully repeat this several times and walk across this pathway. So we've been able to do this in the first round with the GDP mannose, our first kind of intermediate sugar in this pathway. And we've screened about 10,000 reactions, and we've all of single amino acid substitutions within our natural glycosyltransferase. And we found dozens of single amino acid substitutions that perform the chemistry better. And by recombining all those mutations, we've developed double and triple and quadruple mutants that are up to 30 times better at tolerating GDP mannose than the original wild type enzyme. And so we took some of those hyperactive mutants and we asked whether or not those could transfer other sugars, potentially even down the line in our evolutionary pathway, and perhaps even other sugars that we don't describe in the pathway. And this really represents kind of a milestone result in our project, because we were successful in breaking that strict substrate scope, and we can transfer a host of sugars that the natural enzyme can't. What was really exciting is we were able to find triple mutants that are capable of transferring GDP, UDP, and TDP glucose. And these are really milestones because, one, the wild type enzyme can't tolerate these enzymes. Two, glucose actually bears the same stereochemistry that we want in our final sugar. And three, we've actually been able to see some promiscuity relative to the nucleoside diphosphate. So our pathway to our TDP epimycosamine might be sufficient for now, because if we can evolve towards a TDP glucose, that might mean we can ultimately evolve towards the TDP epimycosamine. And so we've now taken those. It puts us in a really unique position now that we've got activity for several different sugars, because now we can continue our directed evolution approach, but instead of just testing on one sugar, we can actually test on all the sugars in our evolutionary pathway and essentially have more routes to our epimycosamine sugar. So in round two, we've kind of shifted away from the random mutagenesis, and given the power of cell-free protein synthesis, we've done all of our engineering in vitro. And we now routinely perform iterative site-saturated mutagenesis on up to 96 residues of our protein. So we continually scan about 20% of the total protein to search for these individual mutations that might increase activity. And then we go kind of step by step, fixing one position at a time until we accumulate multiple mutations that make the enzyme really good for our particular substrate. So one example that I want to share is for the route that we followed for this central sugar, GDP 2-deoxymannose, or we also call it GDP 2-deoxyglucose. It's the same sugar. And these are HPLC traces of kind of different rounds in our evolutionary strategy. And so this purple peak represents our starting material that you see is only present in the really only present in the negative control and the wild type enzyme, where it's not making any product. But after round one, we've discovered a triple mutant that has just a tiny little bit of activity for this sugar, and that's kind of highlighted here in this orange. And then through several rounds, several steps in round two, we've been able to make the enzyme much more efficient at transferring the sugar. And the reason this result in particular is so exciting is because we've not only engineered the enzyme to tolerate a completely new substrate, but we've actually made it fairly good at tolerating that substrate. And that really makes me excited that one day we will be able to find an enzyme that's capable of transferring epimycosamine. And just like the 2-deoxyglucose example, we'll be able to train it to be really good at transferring that sugar. This pipeline also now gives us another unique opportunity. We've collected thousands of data points from a single, double, and triple, quadruple, and so on, mutants, thousands of data points on multiple different sugars. And now we're using another module in our pipeline that uses a deep learning tool called ECNet that was developed by the Zhao and Peng labs at UIUC to try to learn basically design principles for what mutations and what combinations of mutations will give us better activity for one substrate or another. And now that we have these large data sets, we're trying to train them on one sugar and see if they can inform design on another sugar. And we've got very, very preliminary results, but some that suggest that if we train models on mannose, then kind of tweak those models on some data for another sugar, we might be able to predict new mutations or combinations of mutations that are good for that second sugar. And in a way, kind of use one data set for one sugar to learn about another. And so I think that's basically all the time I have. But I'd like to thank everyone in the Jewett lab, everyone in the Eradicate meetings in the Burke lab. Been a phenomenal time working with everybody. Also with the Zhao and Sarab's lab, doing all the machine learning, Doug Mitchell's lab and Satish's lab. Really phenomenal working with everyone. And also thank the audience for your time and attention. Happy to take any questions.
Thank you, John. Due to the time we have, we can take one quick question.